Welcome to the third and final installment of the Electromagnetic Foundation series. My name's John Twardock, and I'll be your host for the interview. Today, we're going to be exploring the phenomenon called electrostatic discharge, or ESD, which is potentially harmful to a wide range of electronic equipment. Our expert guest for the topic is Dr. Kevin-Druis Merenda, who's the product manager for the Ansys EMA3D Charge software. Kevin holds a master's and PhD in physics from L'École Polytechnique in Lausanne, Switzerland, and the Colorado School of Mines, respectively. He studied applied math and astronomy at Boston University and has worked as a research scientist at the European Center for Nuclear Research, also known as CERN. So welcome, Kevin, and thank you for taking time to speak with me today.
Thanks, John. Thank you for having me here today.
All right, well, let's start with some basic principles. What are the conditions that lead to an electrostatic discharge? Describe it, what is it, and why does it happen?
Yeah, so we'll refer to it as an ESD just to make it simpler for the rest of this podcast today. But an ESD typically occurs when there is an electric field which exceeds what we call the breakdown strength of the matter in a certain region. And so it's fundamentally it's a consequence of having high voltages, high currents, having some charges built up in areas where you don't really expect, that will then create a field in a location that will be strong enough to maybe create a spark, create a discharge that you can either typically see, for example, maybe like a spark when you touch your computer and you see a small spark, but also a much bigger spark like a lightning strike, which you can definitely imagine. So these types of discharges are what we would kind of associate to electrostatic discharges.
And what can be done to avoid them then?
So there's a few things. We can typically limit the charging, so the processes that lead up to that ESD. So understanding what kind of currents are present, limit the generation of those currents and this accumulation of charge. This can be done by changing the materials that are present in the system. This can be done by changing the media in the gap where the breakdown actually occurs. There's definitely various ways to tackle these type of situations.
Well, from an engineer or product perspective, what danger does ESD pose to electronic equipment and its design?
Yeah, it can be very dangerous. So there's definitely various ways to mitigate that on electronics equipment. So there's things such as TVS diodes, various types of components that are put on these equipments to deal with transients that are generated from ESDs. And by transient, I mean like a surge of electricity, of current that comes in through the system. And so the consequences, if you don't have the proper mitigation techniques, you're going to completely destroy the electronics equipment, and that will lead to the failure of the whole system that surrounds that equipment.
So it can be complete failure if the charge is significant enough.
Yes, and we've seen issues like this in space applications where there is a spark happening on a gyroscopic system or on a solar panel, and that will break down the whole satellite ultimately because you either can't control the satellite, the mission is a total failure, or even the satellite itself breaks down because of some very large sparks and continuing sparks that would occur from the first breakdown that occurs in the system.
So not a lot of repair shops up there in space for them, I'm sure.
Yeah, yeah, that's pretty limited up there for sure.
Well, I know in talking to Tim McDonald before, we talked about EMI and the amount of regulations there are for testing and passing certification that have to be completed. Is there similar criteria or compliance regulations that engineers face with ESD?
Yeah, so we were just talking about space applications. There's definitely some standards that are imposed by NASA and ESA on the levels of charging that are allowed on the surfaces of these spacecraft or even internally to these equipments. And so these standards are defined in terms of metrics with respect to electric fields and things like that that are need to be analyzed very explicitly with software tools. But in other industries, such as the automotive or the electronics industry, there's also standards that are defined there, such as by the IEC or by the ISO, various organizations that are international that have very specific standards for ESD gun testing, for example.
And are these standards, are they applied the same, or does it vary depending on the serious nature of the design? You know, automotive versus aerospace. I'm sure with aerospace, if it's mission critical, there's no option, you have to pass.
That's right. I think it depends on the type of mission. In space, for example, if it's a human mission, there's no forgiveness there, right? You have to pass. You have to abide by worst case scenarios that exist out there. But if it's maybe a mission that has less stringent constraints, and then maybe you don't actually have to abide by them as much as you would if it was a human-based mission. Maybe there is some incentives in terms of cost. Being able to meet those tests could be difficult, and having solutions such as software could be a way to kind of get away from getting to those, refining those standards in a way that would be more specific to your mission and that would allow you to meet the cost and the budget that you have as a developer.
Can you describe a little bit then the testing that's required here? I mean, what's involved in the test? How time consuming is it, and how expensive is it? I can't imagine it's inexpensive to do this type of test.
Yeah, so it varies on the application, right? So ESDs, the ones that we were talking in the electronics or the automotive industries, we have standardized ESD testing based on ESD guns that you can find relatively easy, right? And so you can actually do a lot of testing, but it requires understanding how the phenomena really occurs. So there is one part of ESD testing that is not fully understood and fully modeled, is that of non-contact discharge ESDs. And these, in testing itself, you can get a lot of those standards done with ESD guns, but sometimes when you want to understand how those non-contact ESDs really affect your electronics, just the testing itself might not be sufficient. And understanding how a PCB reacts under these kind of test standards might require a little more information than just being able to carry out the test, especially if you want to refine the design of the board, things like that. There's a lot going on there where the test itself, just the fact that you got failure or no failure, might not be enough to be able to improve your design. On the space application, it's a little more complex because it's not something people actually can do. Modeling the whole spacecraft in the space environment and understanding how a solar flare will come in and disrupt the charging and the electronics on the system. And so typically this is done by looking at things on a component level in the testing chamber, by approximating the plasma environment that will be available out there, and looking on a much smaller scale, the type of effects that could result from that. And so obviously, we can't test them in space that easily. It's very costly to get an experiment to get the testing going on, and having a simulation capability that would allow you to do these kind of analyses at the full scale is pretty important.
And one last question on the testing. Is it destructive completely most of the time? I mean, are you destroying the design when you test it?
Yeah, I think it really depends on the application, but some applications with respect to radiation environments, like the ones that you find in space, where you're trying to assess the risk of ESD to the charged particles, sometimes those can be definitely destructive, and you can't reuse the sample. Some of the electronics equipments also are typically destructed once you have a flashover or an arc happening on the PCB. It's over for that equipment.
Mm-hmm. Oh, very good. Well, let's talk about an alternative then. talk about the software that you've developed, the Ansys EMA3D Charge. It's described as a charging and discharging modeling solution. Who are the typical users for this?
Right. So we are trying to address the questions that we just discussed here, and the problems we just discussed, and kind of the lack of solution that we just tackled. And so the idea here is that sometimes a software solution is very complementary, if not just the only solution to being able to address these problems of ESDs. And so having the capability to model charging and discharging is important. And so we've done it in two ways. We have a lot of different types of physics in the tool that allows us to kind of tackle the assessment of the risk of ESD. So understanding various interactions between particles and high voltage systems and geometry, and how that leads to fields that could exceed breakdown, as we talked about. But also we have the ability to model the arcing itself. So in some cases, people want to understand how to mitigate the arcing. And so this is where various types of engineers come in, right? So if you just want to see if you're at risk of arcing, we made the module as the simulation suite as easy and as accessible as possible. So typically EMC engineers are the ones that will tackle these problems in the space and defense industry because they need a bit of expertise in terms of plasma physics and electromagnetics. But in some applications, we've made the tool very accessible to mechanical and thermal engineers by putting the tool in Ansys Discovery, which makes it much more accessible in terms of the capabilities and in terms of manipulating CAD and refining CAD to be able to see if a certain gap size, as we've mentioned earlier, or a certain material property would lead to ESD. And so we can really make those workflows more optimal. And so we're trying to make it so that you don't need a PhD in electromagnetics and E&M to be able to do these analyses based on the problem at hand.
Well, if they run the simulation software, what type of predictions or insights can EMA3D Charge provide to them as users? I mean, how do they visualize this? What do they see? I mean, magnetic fields are invisible, right?
Yeah. So as we mentioned earlier, there is those standards that we have that basically put some constraint on various parameters and metrics in the system. And so we're talking a value on the electromagnetic field, for example, or a value on the voltage difference between those electrodes. And conceptually, it might be a little hard to visualize, but the idea is to have a tool that allows you to kind of bring this to the computer screen so that you can then assess visually if you're exceeding these kind of voltages, or if the currents are too high for the system, or even where are the currents traveling and propagating in the system. And so I think this is probably a good time for me to maybe bring up a slide and show you kind of what that looks like visually. So I'll just bring in one example here. So this is kind of an application specific to ESD gun testing and electronics. And so this is our interface here, which is Ansys Space Claim / Discovery, where we have an electronics PCB board, and we are concerned with a non-contact ESD that is generated from an ESD gun. In this case, a lot of the typical softwares will just inject the current in a given location, assuming the location of the breakdown and of the attachment of that discharge. In this case here, we're actually allowing for our tool to simulate the breakdown processes explicitly and not assuming the location of the attachment. And we can then monitor various aspects in addition to the electromagnetic, such as air conductivity or space charge. And what's going to happen here is when we do this breakdown, we have various ways to probe the information, such as the current that is through the arc, or the voltage that is present between the ESD gun tip and the connector. And then we're going to be able to monitor the currents in a very specific location, such as a trace on the other side of this PCB. And so ultimately, this is what it looks like. we have the ESD that is charging up. So we have some fields that are generated onto the PCB, some charges that are building up as well. And then we have the breakdown process where we can monitor the current here as we're looking in amps per meter at the information that we see. And then ultimately, we also look at the induced current as a top view here on the PCB trace. And we can then recover what the peak of that current is. And typically those standards will give you a limit on the transient, okay, like the shape of the waveform that is induced on this trace across the PCB, or maybe the peak of the current on that PCB trace. And these are the type of specs that you can recover from these animations that we have here.
It's very interesting to me because in mechanical simulation, you have to actually model a physical device, but you're modeling not only the package and the surrounding device, but it looks like the air or the medium inside. So maybe walk me through this. One of the really difficult, time-consuming tasks in simulation is importing, creating, cleaning up geometry. Can you walk me through how Ansys EMA3D Charge, how does it tackle that problem?
That's right. So as you just saw, we're basically integrated in a tool called Ansys Discovery. This is a CAD manipulation tool and a CAD cleaning tool. And so what it allows us to do is create and run our electromagnetic simulation on geometry that's imported by the user. So you can either import it, you can create it, and then what we do is we create what's called a numerical mesh on the geometry, which kind of discretizes the geometry in a way that allows us to solve for the electromagnetic fields at any given location in the system. And then when we solve for the electromagnetic fields on that geometry, we can, alongside that, also solve for things such as the plasma information, the velocity of these electrons, the velocity of these ions, and also how many of these ions there are at any given time. And this allows us to explicitly model the breakdown process of air, allows us to model the breakdown of solids, and also to model the various types of complex plasmas and how they interact with the surface of the geometry.
All right, you really got me with a few of those terms there, Kevin.
Was it
Ions.
too much?
No, they're good, but I'm imagining, you said ions and plasma and the breakdown. There's some complex physics involved here. So talk to me about the solvers then. I mean, there are multiple solvers that handle all the physics that are happening in ESD.
That's right.
Can you describe each one of them? Because the number of things you just mentioned cannot be done all with a single solver, I am sure.
Right. So we're reaching this realm of kind of what we refer to as multiphysics simulations, where we not only just solve for electromagnetics, but we solve for hydromagnetics, like the interaction of that ENM with plasmas. We solve for the solvers in terms of basically the plasma itself, or even fluid mechanics even comes in sometimes in some of these applications. So being able to tackle all this is important, and to do that, we developed, like you said, multiple solvers. And so for our applications in air chemistry, like in breakdown of air, as you just saw with the ESD gun, we used what we call a 3D finite difference time domain solver that is full wave. And as the name describes, it's in the time domain. And so this is where we can couple this to basically some what we called fluid conservation equations for modeling the plasma. And so we keep track of those plasma species, like the ions and those electrons, as if in a fluid formulation, which allows us to model it kind of pretty dynamically and alongside the electromagnetic field. We do that, I think, specifically to be able to understand how those ions generate fields themselves, but also how those fields interact with those charged particles, because that co-simulation and that coupling in two ways is very critical to capturing the full picture of these multiphysics solvers and those problems that require these complex solutions. One other application that we have here is the boundary element method and the finite element method. they're two different solvers. They're also electromagnetic solvers, but they're designed to tackle very specific tasks. The former, the BEM, is meant to understand how a plasma induces various types of currents on the surface of the material. And the material in space will react very differently based on some of its properties to the environment that it's in. And so if one material is adjacent to another material and they both behave very differently, they're going to charge with respect to one another differently, and that's going to create a risk for breakdown between the two materials. So you don't even always break down to the environment like the air, but you can also break down between two adjacent surface materials. You can also break down internally to the material itself. And so to tackle the internal breakdown, that's where we developed this finite element method that we coupled with a stochastic tree model to be able to model dielectric breakdown and the treeing effect that you see in dielectrics. And so this applies to solids. It also applies to various types of insulating oils, and it allows us to model basically the path for charge to flow once there was enough voltages to induce breakdown in the system. And then there was one more, I think, that's kind of exciting and interesting. It's our particle transport tool and our particle in cell tool. Basically, what's happening here is that to be able to assess the risk of charging to the point where you get to an ESD, you need to have the right tools to understand how these materials behave under various types of plasmas. And so we have coupled with our electromagnetic solvers these tools that allow us to track high energy charged particles and how they interact with the bulk matter. And depending on their energy, you have very different types of physics that comes in. And so one of them is the 3D particle transport to tackle high energy physics, high energy particles and their interaction with matters. And the other one is the particle in cell tools, which allows us to keep track of various plasma species, typically lower densities, and how they interact with a moving spacecraft, for example.
And where else might something like the particle and cell solver, what other industry, what could that be applied to?
Yeah, so the particle and cell solver, we released it in July for the space application, the space and defense industry. This was meant to be able to understand how the low energy plasma will create charging on 3D geometry, and it will be different because when you have a low energy plasma, those particles, they don't move very quickly and they don't just interact with the surface on their own. The spacecraft moving through that plasma is actually what leads to charging. And because you're going to have an enhanced amount of particles on the front of the spacecraft and then a lack of particles on the back of the spacecraft, this will lead to differential charging between the front and the back that can then lead to ESDs. And so these types of phenomena were very important to capture for the space and defense industry. But it turns out that having this capability of coupling this plasma physics tool with electromagnetics also allows us to do other applications in other industries, such as the semiconductor industry, and more specifically, the plasma-enhanced chemical vapor deposition applications, where you have to model a chamber. In that chamber, there is an influx of a gas, and that gas becomes a plasma under the effect of a radio frequency source. And that plasma then is driven and interacts with the surface of the wafer and leads to chemical interactions on the surface of that wafer. And then you have to be able to handle the byproducts that are also ions and how those interact with the electromagnetic fields. And this process is very complex, and we're trying to fill in a gap here in terms of modeling these types of effects that are not currently something that is available to the community.
That's an incredible range from plasma with spacecrafts down to wafers in the semiconductor industry. So it's a very, very big range, but quite interesting. I have to ask, so I'm a new user then. How hard is it going to be for me to get started? Do I need to be an expert, or what training is available to get me up and running with EMA3D Charge?
Yes, so the applications are are complicated, but we try to make our interface as accessible as possible. And so this comes in two ways. First of all, is to not try to overwhelm the users with many different options to initialize the simulations, try to kind of mitigate the involvement of the users in the numerical stability of the solvers and things like that. But it also comes in providing a lot of help and guidance and tutorials. And so we have step-by-step tutorials. We have a very extensive user manual that describes the physics of these problems. We provide a lot of personalized training to be able to pick up these tools. And we also have something that we've worked on very actively in the past few months, is to develop what we call overlay help in terms of visual, so that we can get some help when we open up a tool. Maybe I can share something with the tool right now to kind of showcase that. Let me see. All right, sorry. So this is kind of, we have Ansys Discovery. And so when we open up a tool such as the domain tool, then we can basically, with the help of a button and press F1 on the keyboard, get a lot of information on instructions of how to use a tool, on typically what is needed from the user as well to set it up. And we have a small video, for example, on how to initialize the specific tool to be usable by our interface properly, and initialize correctly for the solver as well. So that we try to make it easily, so that the learning curve is as minimal as possible.
That looks nice with the help right there available as you're going. Well, it seems to be a somewhat specialized field. Is the overall market demand for ESD and simulation, is that growing? And if so, why?
Yeah, I think ESD has always been a problem. We've always known that it's been a problem, and a lot of ways to address that was through testing. And that's because the processes behind ESDs are complex, right? And to be able to model that physics was always very computationally intensive. And so now that we're reaching levels in computational capabilities that allow us to do these types of models, we're seeing more and more demand in the industry to just be able to simulate these processes, and that becomes very handy to minimize the amount of testing, to refine the type of testing that is being done. So even in places where you can't test, like in space, then having the capability to model that, to be able to make sure that your design is following specifications, then it's always very critical.
Will the current trend toward electrification, electric vehicles, and autonomous, will that also grow the demand for ESD simulation?
Yeah, the more complex those applications are, the more susceptible they become to electromagnetic effects. And so being able to model these various components with very high fidelities, and how they interact under lightning strikes, under ESDs, under like ESD testing, under various types of effects that people need to be able to, that those electronics need to be able to sustain in terms of transients and surges. It's pretty important.
Mm-hmm. Well, it seems like it's a fairly unique solution. Is there anybody else, do you have competition or anyone else that solves this type of problems?
I think I'm not going to say that no one else does some of the capabilities of EMA3D Charge, but what we've tried to do with EMA3D Charge is to encapsulate all these different types of ESDs in one place, and so that we can really understand all the effects that would lead to ESDs, and make it accessible depending on the various types of applications that are thrown towards our customers. And so what can create an ESD is very complex. It's not just a high voltage. It could be an environmental phenomenon like precipitation and rain. It could be a lightning strike. It could be the space plasmas. And so the capabilities that Charge has as a whole is something that you can't find anywhere in the industry, to be able to really model all these types of charging effects in one location in an effective way, with a user interface that is very accessible, such as Ansys Discovery.
What if I'm still skittish as a customer? I mean, do you offer consulting services to get me started? Do you have if I don't have expertise on staff, can an EMA help me?
Yeah, and we understand that. So to take on these tools, there is sometimes a high learning curve. It's difficult, and so one way to get started more easily, is to take on an application that you're familiar with, and try to see how the tool behaves on that specific application. And so EMA has 40 years of consulting experience, and we've been using our tools, the one that we're discussing here today, like EMA3D Charge, for a long, long time. And so we can set up these problems for the customer, and we can then share that with them so that they have something that they are familiar with, that they can take on very quickly and basically start interacting with right away.
Well, great. Well, if I'm a listener here and I have ESD problems, where can I go to learn more about this solution?
Yeah, that's good. So we at Ansys have worked a lot to provide webinars throughout the year, and we have this webinar series that we've been working to put together and to make available to the community. And so a little later this fall, there's a few webinars that are coming to be able to learn more about EMA3D Charge and electromagnetics and software simulations that we have here at EMA. So there's that possibility.
Excellent. Well, thank you again, Kevin, for sharing your expertise with us today. It is absolutely a fascinating, and I'm thinking complex topic, but it's one that seems very critical to the success of so many different electronic designs. For the listeners, again, if you want to expand your knowledge about ESD predictions, register for the workshop that Dr. Merenda spoke of. It's a webcast at the link that's provided again here with this video. Well, this concludes EMA's three-part series on the foundations of electromagnetics and our integrations. Thank you for your attention today, and I hope to see you again on a future broadcast.